Welcome to this course on introductory cosmology. We are going to look into the development of cosmology from the historical point of view in this first lecture. What is the nature of the universe? That is a question which has been haunting us for a very long time. We humans had no idea what was going on in the universe. To help ourselves, we made up stories to help us explain what we saw or to make us feel better about what we didn't understand. Science came to our rescue and we started to understand more. And we could test our ideas, and as we got more confident in the process, our ideas started to grow. The field of cosmology was born to study the cosmos. After centuries of speculation and stories, we are starting to get a grasp of the biggest of ideas. What is the nature of the universe? Let's find out. By the turn of the 20th century, as we know, we had Darwin. Scientists knew the earth was old. Darwin's theory, in fact, talked about the evolution strongly, and it implied that the earth was at least 1 million years old. Then we had Lord Kelvin. He also had a lot of contribution in the field of science. A hugely respected physicist and engineer confirmed the earth was ancient, given that it must have cooled from an initially molten state that takes a while. It logically must be as old or older than the earth. A popular model of the universe was that it was static. It is and always has been as we see it now, and in general hasn't changed. Stars may be born and they may die, but other all things pretty much stayed in balance. The universe always existed, will always have galaxies in it, and they had galaxies in the past. There are variations in on this idea though. In a nutshell, and it's what many astronomers believed, that it's important when we try to understand observation in astronomy, we fit them into a framework of understanding things. So what happens usually is we are connecting the experimental ideas to whatever has been observed throughout the universe. When something doesn't fit, it's a problem. Maybe the observation is wrong, or maybe we are misinterpreting it, or maybe the framework is wrong itself. That's a big step to undertake and needs proper contemplation and skepticism. Science is a tapestry, and when you yank its one thread, the whole thing may need reweaving. Rarely, but sometimes you have to yank that thread. The thread that got pulled in this picture of the universe that we are talking about was uncovered in the year 1912, and it was none other than Vesto Slipher. Well, the name sounds to be a very cool for an astronomer. He actually started taking the spectra of the so-called spiral nebula. What he hoped was to get some insight on their characteristics. Now remember, this was before we understood what galaxies actually were. It took him several years of observation, but by 1917 he had observed 25 of them, and he found something astonishing when he examined the spectra. He saw that almost all of them were highly red shifted. Now the question is, it looked like most of these objects were rushing away from us at speed millions of kilometers per hour. What could that mean at this point? There were two different lines of work that actually began to converge. Now, one was a Belgian theoretical physicist by the name George Lamatter. In the 1920s, he had been studying Einstein's work, the equations. And what was that work we're talking about? The equations dealing with the behavior of the universe. As a whole, Einstein had concluded that the universe was static. But Lamatter would disagree. He found that an expanding or contracting universe fit the equation better, and given the redshift observed by Slipher, he proposed the universe itself was getting bigger, which is why the galaxies appeared to be moving away from us. Then came another brilliant physicist, Alexander Alexander Fredman. He had also reached a similar conclusion. At the same time, astronomers were trying to determine the distances to the nebula, now understood to be the galaxies as their own right. So, galaxies always existed, and some of the very important experimental evidences was provided by Edwin Hubble and his assistant Milton. They were at the forefront of this. What they observed was that the variable stars in the Andromeda galaxy, it allowed them to get the distance to that galaxy. Then they observed some of the same galaxies which Slipher did and measured their distances. When they compared distances to the redshift Slipher observed, they found that further away the galaxy was actually moving at a very fast rate away from us. So more the distance, more was the speed. Let me repeat that because it's kind of important. The further away a galaxy was, the faster it appeared to recede from us. Some other astronomers had also found similar results, but the hard work of Hubble clinched it. We now know it for to be true for every distant galaxy we observe. They all are redshifted, all heading away from us, and this ties into what Lamatter had concluded. The universe expanding. Lamatter himself suggested imagining the cosmic clock running backwards. Galaxies in the sky are getting further and further away from us, but that means that in the past they were close together. Run the clock back far enough and they get closer and closer together until at some point in the past everything in the entire universe was crammed together into an uber dense thing. This is a really weird observation. It's hard to imagine everything in the whole cosmos, every star, nebula, galaxy, every atom, electron, and proton all squeezed together into one infinitely dense blob. But what are these observations telling us? Lamatter called this a primeval atom, or more colorfully, the cosmic egg. Fair enough, but this has implications. If you squeeze all the energy everywhere into one place, that place is going to be hot. When the universe was tiny dot, it would have been unimaginably hellishly hot. Then for some reason it suddenly expanded violently and started cooling. Speed of light is fast, but not infinitely fast. The sun is 150 million kilometers away. It takes light about 8 minutes to reach the earth. So, in a sense, you are seeing the sun as it was 8 minutes ago. Look at this image and maybe you'll be getting some good idea. The nearest star system to us is the Alpha Centauri and it's about 4.3 light years away. So we see it as it was 4.3 years ago. The Andromeda galaxy is about 2.5 million light years away. The light we see from it has now already left the galaxy. This is called the look back time and it's a crucial tool for cosmology by observing very distant objects. We can see the universe when it was young. You might think that we could see all the way back to the moment of the Big Bang. But there's a problem. At some point, Back in time, the universe was so hot and dense that it was the same temperature as the surface of a star it would have been, very luminous but also opaque. As it expanded, it cooled and became transparent if we look back far enough. That moment in time when it cleared up is as far back as we see. What does that moment look like looking at the physics of Big Bang? The maths that describes how matter, energy, space and time behave. Astronomers could predict when this moment happened. In the lifetime of the universe a few 100,000 years after the formation, using the idea of look-back time, they could predict how far away it would be from us and therefore calculate its redshift. The light that reached us billions of years later now should be redshifted into microwave region. Now, in the year 1965, something very peculiar was observed, and that was the cosmic microwave background. Let me tell you a story. In 1965, a pair of radio astronomers announced they had found a signal in their radio telescope that was like a background noise coming from everywhere in the sky. They tried everything they could to explain it, including scrapping out the bird poop inside their radio telescope in case that might be causing it. But the only thing that made sense was that this was indeed the redshifted light from the early universe. They had discovered the glow of the fireball left over from the birth of the cosmos. Later, in the 1990s, satellite observation further refined the measurement of this cosmic microwave background, and now it's essentially confirmed this glow was successfully predicted by the Big Bang model, and now we see it in exquisite detail. Its discovery was a huge step in cosmology. The redshift of distant galaxies and the cosmic background are not the only confirmation we have. The Big Bang model is correct. For example, the model also makes predictions about the elements we see in the universe. At first, when the universe was dense and hot, only subatomic particles could exist, but as the universe cooled for a brief time, they could fuse and form heavier elements. The Big Bang model predicts certain abundances of elements, ratios of them, compared to hydrogen, and that's just what we see in the universe at large. All the sizes and shapes of the largest structure in the cosmos are in line with what a Big Bang model predicts. There's a lot of other observation evidence as well. Galaxies aren't actually doing any moving. It's physically true the galaxies are, for all intents and purposes, standing still in the space. In between them is where all the action is, and it's getting even weirder. This is true no matter what you are in the universe. From any galaxy, it looks like the others are rushing away from you. Look back at that ruler, no matter what tick mark you start with. When the ruler stretches from that spot, it looks like the tick marks are all moving away from you. Big Bang wasn't an explosion in some pre-existing space. It was the initial exploding expansion of space itself. We all have some difficulty with these concepts, but the maths bears them out, and so do essentially all the observations we make of the distant universe. In all this weirdness, don't lose sight of the big picture. The universe had a beginning, and we can see evidence of it. Not only that, but by measuring how quickly it's expanding, we can use maths to run the clock backwards and determine the age of the universe. Currently, the best measurement we have of the age of the universe is 13.8 billion years old. The Big Bang was confirmed when the background radiation glow of the fireball was detected in the year 1960s. Other lines of evidence supported as well. We have measured that the universe is nearly 14 billion years old.